There is a moon orbiting Jupiter right now that is nearly the size of Mercury. Its surface is the most heavily cratered in the entire solar system, a 4.5 billion-year-old record of cosmic violence that has never been erased. It is one of the 4 great moons Galileo discovered in 1610, one of the largest satellites in existence, and a world so enormous it would dominate any conversation if it orbited almost any other planet. But it orbits Jupiter, and because its 3 siblings include a volcanic hellscape, an ice world hiding a global ocean, and the largest moon in the solar system, this giant got quietly forgotten. Its name is Callisto. And the reason everyone overlooked it is the same reason it became one of the most scientifically valuable worlds we can still study. If you enjoy journeys into the overlooked corners of the solar system that change how you see planetary science, consider hitting that like button and subscribing. It genuinely helps this channel keep exploring. Let's begin. There is a world orbiting Jupiter right now that measures 4,800 kilometers across. That is nearly the diameter of the planet Mercury. If you could lift Callisto out of the Jovian system and place it beside Mercury in some cosmic lineup, the two would look almost identical in size, separated by fewer than 60 kilometers of difference. Mercury is a planet. It has been studied, mapped, named in every culture, and visited by dedicated spacecraft. It commands its own chapter in every astronomy textbook ever printed. Callisto is a moon, and most people have never heard its name. This is not a small moon. This is not a captured asteroid tumbling through the outer darkness. Callisto is one of the largest satellites in the entire solar system, ranking 3rd behind only Ganymede and Titan. It is larger than every dwarf planet we have ever catalogued, larger than Pluto by a significant margin, larger than Eris, larger than Marche and Haumea, larger than every single object in the main asteroid belt combined. If this moon orbited the Sun instead of Jupiter, the debate over whether to classify it as a full planet would have started centuries ago and might never have ended. But Callisto does not orbit the Sun, it orbits Jupiter, and that single fact, more than anything else in planetary science, explains why one of the most massive moons in existence became one of the easiest to forget. The story begins on January 7th, 1610, when the Italian astronomer Galileo Galilei pointed a homemade telescope at Jupiter and noticed something strange. 3 faint points of light appeared close to the planet, arranged in a rough line. Over the following nights, he watched them shift positions. A 4th point appeared. The lights moved, but they stayed near Jupiter, orbiting it the way our moon orbits Earth. Within weeks, Galileo confirmed what no one in history had ever proven before. Objects could orbit another planet. Not everything in the sky revolved around Earth. The geocentric model of the universe, already under pressure from the work of Copernicus, cracked open under the weight of 4 tiny moons. These were the Galilean satellites, and their discovery ranks among the most important astronomical observations ever made. A German astronomer named Simon Marius independently observed the same 4 moons around the same time and eventually proposed the mythological names we still use: Io, Europa, Ganymede, and Callisto, each name drawn from figures associated with Zeus in Greek mythology. Each moon destined to become a cornerstone of planetary science over the centuries that followed, but not equally, not even close, and that is where the story begins to fracture. If you have ever watched a documentary about Jupiter's moons, or read a popular science article about the outer solar system, or even glanced at the science section of a news website, you already know the pattern. The conversation begins with Io, because Io is impossible to ignore. Io is the most volcanically active body in the solar system. Not the most active moon, the most active body, period. Over 400 active volcanoes erupt simultaneously across Io's tortured surface at any given time. Rivers of molten sulfur and silicate lava flow across plains stained in shades of yellow, orange, white, and deep red, giving the moon a diseased, mottled appearance unlike anything else in planetary science. Massive eruption plumes shoot material hundreds of kilometers above the surface, arcing through vacuum and falling back down in wide rings of sulfurous frost. Io looks like a world being turned inside out, and in a very real sense, it is. Jupiter's immense gravitational field, combined with the orbital tugging exerted by Europa and Ganymede through their shared orbital resonance, generates tidal forces so extreme that Io's solid body flexes by as much as 100 meters during each orbit. The friction generates enormous internal heat, enough to melt rock throughout much of the interior. Io does not merely have volcanoes. Io is a volcano, resurfacing itself so rapidly that impact craters are almost completely absent. The surface you see today might be only a few million years old, a geological infant compared to the rest of the solar system. Naturally, Io dominates any conversation about Jupiter's moons. But Io is only the first act. Europa's surface is among the smoothest and youngest of any solid body ever observed. Very few impact craters survive on its shell of frozen water because the surface keeps renewing itself. Cracks, ridges, and chaotic terrain crisscross the ice in patterns that strongly suggest it is being broken, shifted, and refrozen from below. Magnetic field measurements from NASA's Galileo spacecraft, which orbited Jupiter from 1995 to 2003, confirmed an induced magnetic signature at Europa that is consistent with a global layer of electrically conducting fluid beneath the ice. The most straightforward explanation is a salty liquid water ocean, possibly containing twice as much water as all of Earth's oceans combined. That ocean appears to sit in direct contact with a rocky seafloor, where hydrothermal vents could drive chemical reactions similar to those that support life in Earth's deep oceans. Europa became the poster child of astrobiology practically overnight. Entire missions have been built around it. NASA's Europa Clipper spacecraft, carrying a price tag of roughly $5 billion, launched in 2024 and is currently en route to Jupiter, with the specific objective of investigating whether Europa's ocean could be habitable. It will arrive at Jupiter in 2030 and conduct dozens of close flybys, each one probing the ice shell, the ocean chemistry, and the geological activity with instruments designed for that single purpose. Europa commands attention because it offers the possibility that life might exist somewhere else in our solar system right now, not in the distant past, not theoretically, but as an active biological system hidden beneath a shell of ice around a gas giant 700 million kilometers away. That possibility alone has driven billions of dollars in investment and shaped the direction of planetary science for the past 3 decades. And then there is Ganymede, the largest moon in the solar system. Larger even than Mercury, though less massive due to its ice-rich composition. Ganymede holds a title no other moon can claim. It is the only satellite in the solar system known to generate its own intrinsic magnetic field, produced by convective motions in a liquid iron core. This means something dynamic and sustained is happening deep inside Ganymede, an internal engine still running after billions of years. Ganymede also shows strong evidence for a subsurface ocean, possibly sandwiched between layers of ice at different pressures deep within its interior. Its surface tells a story of geological evolution, split between ancient, heavily cratered dark terrain and younger, tectonically grooved bright terrain that suggests the moon resurfaced significant portions of itself at some point in its past. Ganymede is a world that changed. It evolved. It partially erased its own early history and replaced it with something new. Io has volcanoes. Europa has an ocean and the possibility of life. Ganymede has a magnetic field and the crown of largest moon in existence. Each one offers a dramatic headline. Each one commands immediate scientific and public attention through qualities that are vivid, visceral, and easy to communicate. And then, at the end of every list, mentioned almost as an afterthought, comes Callisto. Callisto orbits farthest from Jupiter among the 4 Galilean moons, approximately 1,880,000 kilometers from the planet's cloud tops. That distance is not just a number, it is a geological destiny. Io, Europa, and Ganymede are locked into a precise orbital resonance called the Laplace resonance. For every single orbit Ganymede completes around Jupiter, Europa completes exactly 2, and Io completes exactly 4. This mathematical relationship is not a coincidence. It is a gravitational engine. The resonance continuously pumps tidal energy into all 3 moons, flexing their interiors, generating heat, and driving the geological activity that makes each one so distinctive. Io gets volcanism. Europa gets a liquid ocean beneath a flexing ice shell. Ganymede gets enough internal heat to maintain a molten iron core and an intrinsic magnetic field. Callisto sits outside this resonance entirely. It orbits beyond the gravitational dance floor, unaffected by the tidal engine that powers its three siblings. No resonance means no significant tidal heating. No tidal heating means no internal engine driving volcanism or tectonics. No volcanism or tectonics means no surface renewal. Callisto is the sibling who was not invited to the party, and the surface it carries today reflects that exclusion with absolute clarity. When NASA's Voyager 1 and Voyager 2 spacecraft flew past Jupiter in 1979, they returned images of all 4 Galilean moons. The images of Callisto showed a surface absolutely saturated with impact craters. Craters on top of craters on top of craters. No smooth plains, no grooved terrain, no lava flows, no fracture systems suggesting internal stress. No evidence of any geological process beyond impacts from space. Just a battered, ancient, uniformly cratered world stretching from horizon to horizon in every image the cameras captured. Scientists at the time were not particularly inspired. Some described Callisto as an ugly duckling, a phrase that stuck in the literature and popular memory for decades. Others called it a dead moon, a hunk of rock and ice that had done nothing interesting since the solar system formed. Compared to the volcanic fury of Io, the astrobiological promise of Europa, and the sheer record-breaking scale of Ganymede, Callisto seemed like a world where nothing had ever happened and nothing ever would. It became the 4th Galilean moon in every sense, the one listed last, mentioned briefly, and moved past without pause. That dismissal proved remarkably durable. For decades, Callisto occupied a strange position in planetary science, too large to truly ignore, too apparently inactive to generate excitement. It appeared in textbooks as a comparison point, a baseline for what a geologically dead icy moon looks like. Researchers studied it, catalogued its craters, measured its density, its reflectivity, its surface composition. They published papers and attended conferences, but the energy, the funding, the mission proposals, the public fascination, the documentary airtime, all of that flowed relentlessly toward Callisto's more dramatic siblings. Callisto became planetary science's quiet room in a house full of screaming children. But here is what makes this overshadowing so remarkable. Callisto is not small, it is nearly 5,000 kilometers in diameter, carrying roughly 1/3 the mass of Mercury despite having nearly the same diameter, owing to its ice-rich composition rather than Mercury's dense metallic interior. If you lifted Callisto out of the Jovian system and dropped it into the inner solar system as an independent body orbiting the Sun, only the 4 rocky planets and 2 fellow moons, Ganymede and Titan, would exceed it in diameter among the solid worlds. It would outrank every dwarf planet, every asteroid, every comet nucleus ever discovered. It would be a major world by any reasonable definition. And yet, because it shares an orbital neighborhood with 3 moons that each possess one single dramatic quality, Callisto slid into the background. This reveals something important about how we allocate scientific attention and public interest. We are drawn to spectacle. A volcano commands attention because it represents active destruction, forces at work, energy being released, landscapes being transformed in real time. An ocean hidden under ice commands attention because it represents the possibility of life, the most emotionally charged question in all of science. A record-breaking size commands attention because humans instinctively notice superlatives. Biggest, smallest, hottest, fastest. Quiet preservation does not compete well against these hooks. Even when the quiet world is nearly the size of a planet, Callisto did not lose the spotlight because it lacked scientific value. It lost the spotlight because its value is not loud. Consider what Callisto actually is when you set aside the comparison to its siblings. It is a body composed of roughly equal parts rock and ice by mass, with an overall density of approximately 1.83 grams per cubic centimeter. That density, combined with gravity measurements from the Galileo spacecraft, tells scientists something extraordinary about Callisto's interior. Unlike Ganymede, which fully differentiated, meaning its heavier, rocky and metallic materials sank to the center, while lighter ices rose to the top, Callisto appears to have remained only partially differentiated. its rock and ice may never have fully separated into distinct layers. This means Callisto's interior retains something close to its original primordial composition, a state that no other large moon or planet in the solar system preserved. Its surface temperature hovers around -139 degrees Celsius on the sunlit hemisphere, dropping even colder on the night side. It possesses an extremely thin atmosphere, barely detectable, consisting primarily of carbon dioxide at surface pressures measured in trillionths of a bar. This is not an atmosphere in any functional sense. It is a whisper, a trace presence likely sustained by the slow release of gas from surface ice under ultraviolet radiation from distant sunlight. And the surface itself is ancient beyond easy human comprehension. When planetary scientists describe Callisto's terrain as old, they do not mean old the way a mountain range on Earth is old. Earth's oldest exposed surface rocks date to roughly 4 billion years. The Moon's ancient highlands approach 4.5 billion years. Callisto's cratered plains match that extreme. They date to approximately 4.5 billion years ago, to the very earliest era of the solar system's formation. Some estimates push portions of the surface record back to within the first 100 million years of Callisto's existence. Every other large world in the solar system has erased or severely modified its early surface record. Earth's crust is perpetually recycled. Venus was catastrophically resurfaced. Mars retains some ancient terrain, but even those surfaces have been modified by billions of years of erosion and volcanic activity. Our Moon preserves ancient highlands, but enormous regions were flooded by mere basalts between 3 and 4 billion years ago. Ganymede resurfaced roughly 2/3 of its terrain with tectonically grooved bright material. Only Callisto kept everything, because nothing internal ever happened powerful enough to erase it. Callisto did none of this. It kept everything. Every impact scar from the earliest bombardment era, every crater from the billions of years that followed, every ring structure from the largest collisions, all of it is still there. The record was never overwritten. The archive was never reformatted. The tape was never recorded over. And that is where the real scientific importance begins to emerge. The irony embedded in Callisto's story is almost too clean. The same qualities that made it scientifically forgettable, no volcanism, no tectonics, no dramatic surface renewal, are exactly the qualities that made it one of the most scientifically irreplaceable objects in the solar system. A world that never erased its past became a world where the past is still perfectly readable. A moon that never produced a single headline-worthy geological event preserved the most complete record of what happened to it during the most violent era in solar system history. But appreciating this requires a shift in perspective that does not come naturally to most people, including many scientists. We are neurologically wired to notice change, motion, danger, spectacle. A volcano erupting on Io triggers an immediate response. An ocean hiding beneath Europa's ice triggers imagination and hope. A record being broken by Ganymede's sheer size triggers our instinct for superlatives. Quiet preservation, the simple act of keeping a surface unchanged for 4.5 billion years, does not trigger any of those responses. It requires you to think rather than react, to understand why an unchanged surface is extraordinary rather than boring. And then came the twist that should have changed the conversation entirely. During the Galileo mission's flybys of Callisto in the late 1990s, the spacecraft's magnetometer detected something unexpected. An induced magnetic field, similar in character to the one that had confirmed Europa's subsurface ocean, though weaker and more ambiguous. The signal was complicated by Callisto's surprisingly dense ionosphere, which could potentially mimic some of the magnetic signatures that a conducting subsurface layer would produce. For more than 2 decades, scientists debated whether the magnetic data truly required an ocean beneath Callisto's ice, or whether the ionosphere alone could account for the measurements. The question remained genuinely unresolved, caught between 2 plausible interpretations. Then, in early 2025, a research team led by Corey Cochrane at NASA's Jet Propulsion Laboratory published a landmark study in the journal AGU Advances. The team applied advanced statistical techniques to magnetic data from multiple Galileo flybys, incorporated detailed computational models of Callisto's ionosphere, and ran tens of thousands of forward models of the Moon's possible interior configurations. Their conclusion was striking. The ionosphere alone cannot explain the observed magnetic induction signal. The evidence much more strongly supports the existence of a subsurface salty ocean beneath Callisto's thick ice shell, possibly located more than 100 kilometers below the surface. The forgotten moon, the dead moon, the boring one at the end of every list, very likely hides a liquid water ocean. But this finding did not catapult Callisto into the public spotlight. There was no headline dominating international news. No animated graphics of Callisto's hypothetical ocean went viral across social media. The paper was covered by specialist outlets, discussed within the planetary science community, and quietly noted by researchers who study the Jovian system. In the broader public conversation about space, it barely registered. Even Callisto's most dramatic revelation arrived quietly, almost as if the moon itself refused to make a scene. That quiet is exactly the thread we need to follow next. Because Callisto's surface, the most heavily cratered in the entire solar system, is not merely old, it is a specific kind of old that no other large world preserved. Every impact scar on that battered terrain carries encoded information about what was hitting Jupiter's moons billions of years ago, how large those impactors were, how frequently they arrived, and what the early outer solar system looked like during the most violent chapter of its formation. What Callisto kept, while every other giant world was busy erasing its own history, turns out to be one of the most complete records of ancient planetary bombardment that still exists anywhere in the solar system. And reading that record changes what we thought we knew about the deep past. When the first detailed images of Callisto arrived on Earth from the Voyager flybys in 1979, the scientists studying them faced a surface unlike anything they had encountered on any other large world. Every square kilometre appeared cratered. Not partially cratered, not cratered in patches with smooth plains between them, but universally, exhaustively, relentlessly cratered across the entire visible globe. Large craters sat beside medium craters, that sat beside small craters that overlapped with ancient degraded craters whose rims had been battered into barely recognizable ridges by subsequent impacts that had themselves been partially obliterated by still later strikes. The entire surface looked like it had been subjected to an artillery bombardment lasting billions of years, which is precisely what happened. Planetary scientists use a specific term for what they were seeing: crater saturation. A surface reaches saturation when it has accumulated so many impact craters that adding a new one necessarily destroys or partially erases an older one. There is no empty space left. Every patch of ground has already been hit. The terrain cannot record additional impacts without losing information about previous impacts in the process. Think of a library where every shelf is full. You can still add a new book, but only by removing an old one to make room. The total count stays roughly constant, even as the collection keeps changing. Callisto's surface has reached that state across nearly its entire extent, and the implications are staggering. Crater saturation means the surface is ancient beyond the capacity of cratering alone to date it precisely. Once a surface reaches saturation, the crater density stops increasing with time. A surface that saturated 3 billion years ago looks statistically similar to one that saturated 4 billion years ago. The clock effectively stops. Scientists can determine that the surface is extremely old, but pinning down exactly how old requires additional analysis, modelling of cratering rates, comparison with other bodies, and careful study of the largest impact features that take longest to reach equilibrium. Based on theoretical models and comparisons with the lunar cratering record, the consensus places Callisto's cratered plains at approximately 4.5 billion years old, dating to the earliest era of the solar system. No other body of comparable size preserves a surface this ancient. Earth's crust is perpetually recycled. Venus was catastrophically resurfaced. Mars retains some ancient terrain modified by billions of years of erosion. Our moon's highlands were partially buried by mare basalts. Ganymede resurfaced roughly 2/3 of its terrain with grooved, bright material. Only Callisto kept everything. Because nothing internal ever happened powerful enough to erase it. This absence of internal geological activity is not an accident. It is a direct consequence of Callisto's position in the Jovian system. Orbiting beyond the Laplace resonance that drives tidal heating in Io, Europa and Ganymede, Callisto receives no significant tidal energy from Jupiter. Its interior never experienced the forced flexing that melts rock inside Io or maintains liquid oceans beneath the ice shells of Europa and Ganymede. Without that energy input, Callisto's only heat source was the decay of radioactive elements within its rocky component, a process that generates far less heat than tidal forcing and diminishes steadily over time as the radioactive isotopes decay. That modest internal warmth was never sufficient to drive volcanism, fracture the ice shell with tectonic stresses, or trigger the kind of global resurfacing event that would have erased the ancient cratered terrain. The result is a world where the surface is essentially a fossil. Not a fossil in the biological sense, but a fossil in the geological sense, a preserved record of conditions and processes that existed billions of years ago but no longer operate. Every crater on Callisto is a data point. Its size encodes information about the mass and velocity of the object that created it. Its morphology, whether it has a simple bowl shape, a central peak, a central pit, or a flat floor, encodes information about the mechanical properties of the surface at the time of impact and the energy involved in the collision. The physics of how these craters form on Callisto differs in important ways from how they form on rocky bodies like the Moon or Mercury, and those differences carry scientific information that is unique to icy targets. When a high-velocity impactor strikes a rocky surface, the energy of the collision is partitioned into shock heating, excavation, and fracturing of the surrounding crust. The crater reaches its maximum depth within seconds, after which the walls collapse inward and the compressed floor rebounds upward, producing central peaks and terraced rims. Decades of lunar and terrestrial impact studies have calibrated the relationship between impactor properties and crater morphology for rocky surfaces. Callisto's surface is not rock. It is a mixture of water ice and rocky material, and ice behaves very differently from silicate rock under impact conditions. Ice is less dense, mechanically weaker at the temperatures relevant to Callisto's surface, and capable of undergoing phase transitions that rock does not experience during cratering events. When a large impactor strikes Callisto, the shock wave propagates through a target that is part crystalline ice, part rocky debris, and part void space where the two components meet imperfectly. The excavation process mobilizes material that may include pockets of volatile rich ice that behave almost like a fluid under the transient pressures of the impact event. The collapse dynamics that shape the final crater are governed by the viscosity and strength of an ice-rock mixture rather than solid silicate, producing crater morphologies that are systematically different from those on rocky worlds. This is why the central pit craters on Callisto, those in the 25 to 100 kilometer diameter range, are so scientifically interesting. Central pits do not form on rocky bodies under normal conditions. They appear to require a target material where volatiles can be mobilized during the crater collapse process, either through impact-induced melting of ice or through the release of trapped gases within a porous ice rock matrix. The depth, diameter, and morphology of these central pits vary systematically with crater size on Callisto, and that variation traces the mechanical properties of the crust at different depths. Researchers can use the pit characteristics as indirect probes of subsurface structure, inferring where the ice-to-rock ratio changes, where temperatures increase enough to soften the material, and where the transition from brittle to ductile behavior occurs within the crust. Valhalla and Asgard carry this ice target physics to its extreme. Multi-ring basins form when impacts are so energetic that the shock waves propagate through the entire lithosphere, the rigid outer shell of a body, and interact with weaker material beneath. On the Moon, multi-ring basins like Orientale formed when the impact penetrated through the rigid crust and excavated into a zone where temperatures were high enough for the rock to flow slowly, allowing concentric rings to form as the crust collapsed inward around the excavation cavity. On Callisto, the lithosphere is ice, and the weaker substrate beneath it may be warmer ice, a slush layer, or potentially the upper boundary of the hypothesized subsurface ocean itself. The specific pattern of concentric rings at Valhalla, their spacing, their number, their degree of tectonic displacement, encodes information about the mechanical layering of Callisto's outer shell at the time of the impact. Reading that information requires models calibrated to ice target physics, rather than the rocky body models developed for lunar and terrestrial craters. Callisto's multi-ring basins are not simply larger versions of lunar impact structures. They are fundamentally different phenomena, formed in a fundamentally different material, and they record information about icy body crustal structure that cannot be obtained from any rocky body crater record. Its degradation state, how eroded and softened its rim appears, encodes information about how long it has been exposed to the slow processes that gradually modify features on an airless icy surface. Processes like sublimation of ice, mass wasting of crater walls, and bombardment by micrometeorites. Callisto's craters form a statistical population that tells a story about the history of impactor flux in the outer solar system. How many objects were striking the Jovian moons during different epochs? How large those objects were, whether the impactors were primarily comets or captured asteroids, whether the bombardment rate was constant or punctuated by spikes corresponding to planetary migration or the destabilization of distant small body reservoirs. This kind of analysis is called crater counting, and it is one of the oldest and most powerful tools in planetary science. By measuring the size-frequency distribution of craters on a surface, meaning how many craters of each size exist per unit area, scientists can estimate the age of that surface and reconstruct the bombardment history it experienced. The technique has been calibrated using lunar samples returned by the Apollo missions, which provided absolute radiometric ages for specific surfaces on the Moon. By matching those absolute ages with the crater densities observed on those same surfaces, researchers established a relationship between crater count and age that can be cautiously extended to other bodies in the solar system. Applying this technique to Callisto reveals something remarkable. The crater population on Callisto's oldest terrain does not precisely match the crater population on the Moon's oldest terrain. The size distribution is different. Callisto shows a relative deficit of small craters compared to what the lunar record would predict if both bodies experienced the same impactor population. This difference has been interpreted as evidence that the impactors striking the Jovian moons were drawn from a different source population than those hitting the inner solar system. Specifically, the outer solar system bombardment appears to have been dominated by cometary objects arriving from reservoirs beyond Jupiter, objects with different size distributions and velocity characteristics than the asteroids that primarily bombarded the Moon and the inner planets. Understanding why this distinction matters requires stepping back to consider what planetary scientists actually learn from crater populations. When researchers count craters on a surface and sort them by size, the resulting distribution follows a mathematical curve. The shape of that curve is not random. It directly reflects the size distribution of the objects doing the impacting. A population dominated by small impactors produces many small craters relative to large ones, creating a steep curve. A population with a higher proportion of large impactors produces relatively more large craters, flattening the curve. The shape of the curve is a fingerprint of the impactor source. On the Moon, the crater size frequency distribution has been calibrated against absolute ages from Apollo samples. That calibration reveals a specific curve shape that reflects the asteroid population of the inner solar system. Objects originating primarily from the main asteroid belt between Mars and Jupiter, perturbed into planet-crossing orbits by gravitational interactions with Jupiter and the terrestrial planets. These asteroids follow a well-characterized size distribution, with a particular ratio of small to large objects. When scientists use the lunar curve to predict what Callisto's crater population should look like if it experienced the same impactor population, the prediction fails. Callisto has proportionally fewer small craters and a different slope to its size-frequency distribution, particularly at diameters below about 10 kilometers. This mismatch has profound implications. It means the objects hitting the Jovian moons were fundamentally different from the objects hitting the Moon. The leading interpretation identifies Jupiter family comets as the dominant impactor population in the outer solar system. These comets originate from the scattered disk and the Kuiper belt, reservoirs of icy bodies beyond Neptune that are gradually perturbed inward by gravitational interactions with the giant planets. When these comets enter the Jovian system, Jupiter's enormous gravity accelerates them to high velocities, but the intrinsic size distribution of cometary nuclei differs from the size distribution of main belt asteroids. Cometary populations appear to be deficient in small bodies relative to asteroids, producing the observed deficit of small craters on Callisto's surface. This finding is obtainable only from the Jovian moon crater record. The inner solar system crater populations are dominated by asteroidal impactors, and the cometary contribution there is difficult to isolate from the dominant signal. Mars, the Moon, and Mercury all record the asteroidal bombardment story. Only bodies in the outer solar system, far enough from the asteroid belt for cometary impactors to dominate, record the cometary bombardment story in clean form. And among outer solar system bodies large enough to preserve a statistically meaningful crater population across all relevant size ranges, Callisto stands alone in having never resurfaced. Ganymede's grooved terrain erased 2/3 of its record. The Saturnian moons are mostly too small or have been partially resurfaced by cryovolcanic activity. Callisto kept the full cometary bombardment ledger, from the smallest countable craters to the largest multi-ring basins, uninterrupted across 4.5 billion years. This is not merely an academic distinction. The size distribution of comets tells scientists about the physical processes that shaped small bodies in the outer solar system, the collisional evolution of the Kuiper belt, the efficiency of fragmentation in icy materials versus rocky materials, and the dynamical history of the giant planet region during the epoch when the solar system's architecture was still being established. Each of these questions connects to the larger problem of how planetary systems form and evolve, a question with direct relevance to understanding the thousands of exoplanetary systems now being discovered around other stars. Callisto's crater population is a window into that history, and it is the only window of its kind that has not been shuttered by geological activity. This distinction matters enormously for understanding solar system history. One of the most debated questions in planetary science involves the late heavy bombardment, a hypothesized spike in the impact rate across the inner solar system, approximately 700 million years after the planets formed, roughly 3.9 billion years ago. Evidence for this spike comes primarily from the clustering of radiometric ages in lunar samples and from the observation that many of the Moon's largest impact basins appear to date from a narrow time window. Some models propose that the late heavy bombardment was triggered by a major orbital rearrangement among the giant planets, where Jupiter, Saturn, Uranus, and Neptune shifted positions, and in the process, destabilized vast populations of small bodies that were then flung throughout the solar system. If such an event occurred, it should have affected the Jovian moons as well as the inner planets. Callisto's crater record provides one of the best tests of this hypothesis. Detailed analysis of the largest multi-ring impact structures on Callisto, particularly Valhalla and Asgard, allows scientists to estimate when the most energetic impacts occurred and whether they cluster in time the way late heavy bombardment models predict. The ages of these structures remain debated, with estimates ranging from approximately 1 to 4 billion years depending on the assumed background cratering rate. But the statistical properties of the overall crater population provide constraints on whether the bombardment rate was smooth or punctuated, and those constraints feed directly into models of how the outer solar system evolved dynamically during its first billion years. Valhalla is the feature that anchors this entire discussion. It is the largest clearly identified impact structure on Callisto, and one of the largest preserved impact features on any body in the solar system. At its center sits a bright region roughly 600 kilometers across, surrounded by a system of concentric rings that extends outward to a diameter of approximately 3,000 kilometers. That ring system is wider than the distance from Los Angeles to Denver. Standing at the center of Valhalla and looking outward, the rings would stretch beyond the horizon in every direction, fading into the cratered terrain like ripples frozen in ice. The formation of Valhalla involved an impact of extraordinary energy. An object likely tens of kilometers across struck Callisto's ice rock surface at velocities of tens of kilometers per second. The collision excavated a massive crater, and the shock waves from the impact propagated outward through the icy crust, fracturing it into the concentric ring pattern that survives today. The central bright region may represent the zone where the impact excavated deep enough to expose relatively cleaner ice from beneath the surface's accumulated layer of dark, radiation-processed material. What makes Valhalla scientifically important is not just its scale, but its preservation. On any geologically active world, a structure this large would have been modified, partially buried or entirely destroyed by subsequent geological processes within a few 100 million years. On Earth, a 3,000-kilometer impact structure would be obliterated by plate tectonics in a single Wilson cycle. On Ganymede, The formation of grooved terrain overprinted and disrupted many of the oldest large impact features. On Callisto, Valhalla sits largely intact, degraded only by the slow accumulation of later impact craters superimposed on its rings and the gradual viscous relaxation of topographic relief in the icy crust over billions of years. Asgard is the second largest multi-ring structure on Callisto, measuring approximately 1,600 kilometers in diameter. Like Valhalla, it consists of a central bright region surrounded by concentric ring scarps, though its ring system is less extensive and somewhat more degraded. Together, Valhalla and Asgard demonstrate that Callisto experienced at least two impacts of genuinely catastrophic scale during its early history, events energetic enough to fracture the crust across continental distances, and that both events left permanent marks that have survived to the present day. These structures offer something that almost no other surface in the solar system can provide: a direct record of the largest collisions that occurred in the Jovian system during the epoch of heavy bombardment. Smaller craters are useful for statistical analysis, but the largest impacts are the ones that constrain the upper end of the impactor size distribution and the most energetic events in early solar system history. Because Callisto preserved these structures while Ganymede's resurfacing destroyed or obscured its equivalent features, Callisto holds information about the bombardment environment around Jupiter that simply does not exist anywhere else. Beyond the giant multi-ring structures, Callisto's surface reveals subtlety that the early characterization of Ugly Duckling entirely missed. The craters themselves come in a carefully organized morphological sequence that reflects the physics of impact into an ice rock surface. The smallest craters, those with diameters below approximately 5 kilometers, have simple bowl shapes, consistent with formation in a relatively strong surface layer. Craters in the 5 to 40 kilometer range typically display central peaks formed when the compressed material at the base of the transient crater rebounds upward after the impactor's energy dissipates. Larger craters, spanning roughly 25 to 100 kilometers, often feature central pits rather than peaks, a characteristic specific to impacts into ice-rich targets where subsurface volatiles may have been mobilized during the crater's formation. The very largest craters, above 60 kilometers, sometimes show central domes, interpreted as the result of tectonic uplift of deep material during the post-impact collapse of the transient cavity. This morphological progression carries information about the vertical structure of Callisto's crust. The transition from central peaks to central pits to central domes reflects changes in the material properties at different depths. At shallow depths, the crust behaves like cold, rigid ice rock mixture. At greater depths, the material becomes warmer and mechanically weaker, allowing different collapse dynamics during crater formation. By studying where these transitions occur as a function of crater size, scientists can infer the thermal gradient within Callisto's crust, which in turn constrains models of the Moon's internal heat flow and thermal evolution. The surface also reveals something unexpected about the very smallest scales. High-resolution images from the Galileo spacecraft showed that Callisto's terrain lacks the small craters below, about 1 kilometer in diameter, that bombardment models predict should be present in enormous numbers. Instead, at the smallest scales, the surface appears smoothed and mantled by a layer of dark, fine-grained material that blankets the underlying topography. This mantling layer is thought to result from a process called sublimation degradation. Over billions of years, exposure to sunlight and charged particle radiation from Jupiter's magnetosphere slowly erodes the ice component of Callisto's surface through sublimation, the direct conversion of solid ice into water vapor that escapes into space. What remains behind is a lag deposit of dark, non-ice material, rocky dust and organic compounds that originally were mixed into the ice but concentrated at the surface as the ice disappeared. The process operates on timescales that are almost impossible to visualize. Each year, a microscopically thin layer of surface ice transitions directly from solid to vapor under the feeble warmth of sunlight at Jupiter's distance, roughly 5 times farther from the Sun than Earth. The sublimated water molecules drift away from the surface at low velocities, most of them escaping Callisto's modest gravity entirely and dispersing into the surrounding space or falling back far from their point of origin. What stays behind is the non-volatile component, the dark silicate grains, the carbonaceous particles, the radiation-processed organic residue that was trapped within the ice matrix when the surface material was originally deposited. Grain by grain, century by century, this dark residue accumulates into a lag deposit that eventually forms a continuous blanket over the original icy terrain. The thickness and maturity of this lag deposit varies across the surface, in ways that encode time and exposure history. Regions that have been exposed to sunlight and radiation for the longest periods without interruption by fresh impacts carry the thickest, darkest lag. Regions where a recent impact excavated through the lag and exposed fresh subsurface ice appear as bright patches or ray systems that stand out sharply against the darker surrounding terrain. Over time, those bright patches themselves darken as the sublimation cycle begins working on the newly exposed ice, gradually building a new lag layer over the fresh material. The rate at which a bright ray crater fades toward the background darkness provides an independent constraint on the sublimation rate, giving scientists a clock of sorts for measuring how quickly Callisto's surface evolves through this process. This two-layer structure, dark lag over bright ice, transforms every fresh crater into a probe of subsurface composition. The material excavated by an impact comes from below the lag, where relatively unprocessed ice still exists. Spectroscopic measurements of bright crater ejecta reveal water ice signatures that are largely absent in the surrounding dark terrain, confirming that the darkening is a surface phenomenon rather than a compositional one. The bulk of Callisto's crust remains ice-rich. Only the outermost skin has been chemically processed into darkness by billions of years of radiation exposure and sublimation concentration. The lag deposit also explains a feature that puzzled early researchers. Callisto's overall albedo, its reflectivity, is significantly lower than that of the other Galilean moons. Despite having a broadly similar ice rock composition, Europa, whose surface is geologically young and continually refreshed, reflects roughly 67% of incoming sunlight. Ganymede, with its mix of old and young terrain, reflects about 43%. Callisto reflects only about 22%, making it one of the darker large bodies in the outer solar system. Early interpretations suggested that Callisto might simply contain less ice than its siblings, but the bright crater exposures and spectroscopic evidence confirmed that ice is abundant just below the surface. The darkness is not compositional poverty, it is the signature of age, the accumulated residue of billions of years of surface processing on a world that never produced a geological event capable of wiping the slate clean and exposing fresh ice on a large scale. This sublimation lag explains why Callisto is the darkest of the Galilean moons despite being composed of significant amounts of water ice. The bright ice is there, but it is buried beneath a coating of dark residue that accumulated over billions of years of slow surface processing. Wherever a fresh impact excavates through the dark lag and exposes clean ice from below, the crater appears as a bright spot against the darker surrounding terrain. These bright ray craters are scattered across Callisto's surface, providing direct evidence that relatively pure ice exists just below the dark veneer. The interplay between impact cratering and sublimation erosion creates a complex surface that is far more scientifically informative than the initial impression of monotonous cratering suggested. Each crater preserves information about the impact event that created it. The dark mantling material preserves information about billions of years of surface environment interaction. The bright patches where fresh impacts have penetrated the lag preserve information about subsurface composition. The morphological transitions preserve information about crustal structure and thermal state. But here is the truth. Callisto's surface is not a featureless wasteland of ancient battering. It is a layered archive of processes spanning the entire age of the solar system. And here is the critical point that separates Callisto from every other heavily cratered body we can study. The Moon is ancient and heavily cratered, but its surface was partially overwritten by mere volcanism, and its cratering record is calibrated by Apollo samples that anchor it to the inner solar system's impactor population. Mercury is ancient and cratered, but its surface experienced volcanic flooding of its own, and it orbits in a completely different dynamical environment than the Jovian moons. The Saturnian moons are icy and cratered, but most are too small to have preserved the largest impact structures intact, and their cratering records are complicated by the different impactor populations present in the Saturnian system. Mars retains ancient cratered terrain, but atmospheric erosion and dust deposition have degraded many features. Callisto occupies a unique position. It is large enough to have experienced and preserved the full range of impact sizes, from sub-kilometer craters to 3,000-kilometer multi-ring basins. It is ancient enough that its surface samples the bombardment record all the way back to the formation of the Jovian system. It is geologically dead enough that nothing internal has ever overwritten the record, and it orbits in the Jovian system, meaning its cratering record samples the outer solar system impactor population, which is dominated by cometary objects rather than the asteroids that dominate the inner solar system record. No other single body combines all four of these characteristics. Callisto's surface is not merely old, it is the most complete surviving record of outer solar system bombardment history that exists anywhere. This is why calling Callisto boring represents such a fundamental misunderstanding. The boredom that observers project onto this moon arises from the absence of active geological processes. Volcanoes, geysers, shifting plates, erupting plumes. These processes are visually dramatic and scientifically exciting in their own right, but their presence on a world invariably means destruction of the old surface record. Every lava flow that covers a cratered plain destroys information about the impacts that occurred there. Every tectonic event that fractures and displaces crustal blocks disrupts the spatial relationships between craters that allow statistical dating. Every episode of resurfacing reformats the archive and starts the clock over. Callisto never reformatted. The original data is still there, written in a script of impact craters that planetary scientists are slowly learning to read with increasing precision. Each improvement in imaging resolution, each refinement in cratering models, each new comparison with the bombardment records of other worlds reveals additional information encoded in Callisto's battered terrain. The surface that early scientists dismissed as uninteresting turned out to be one of the most information-dense surfaces in planetary science, precisely because nothing ever happened to degrade that information. The contrast with Ganymede sharpens this point. Ganymede and Callisto are nearly twins in size and bulk composition. Both are roughly half rock and half ice by mass. Both formed in the same circumplanetary disk around Jupiter at approximately the same time. Both experience the same early bombardment environment, yet they look completely different. Ganymede's surface is divided between ancient dark terrain that resembles Callisto's cratered plains and younger bright terrain, cut by elaborate systems of parallel grooves and ridges. The bright terrain covers roughly 2/3 of Ganymede's surface and clearly formed later, overprinting the older cratered material. Whatever drove the formation of Ganymede's grooved terrain, whether it was tidal heating from the Laplace resonance, internal differentiation releasing gravitational energy, or some combination of factors, it erased the bombardment record across most of Ganymede's surface. The dark terrain that survives on Ganymede is scientifically valuable, but it covers only about 1/3 of the Moon, and has itself been modified by proximity to the tectonically active bright terrain. Ganymede cannot tell us what Callisto can tell us, because Ganymede chose spectacle over preservation. It resurfaced itself. It produced geological drama, and in doing so, it destroyed most of the ancient record that Callisto kept intact. This is the quiet inversion at the heart of Callisto's story. The same geological inactivity that made it seem boring is the mechanism that preserved its scientific value. The same absence of internal heat that prevented interesting surface features from forming is what prevented those features from destroying the bombardment record. Callisto's lack of drama is not a failure. It is a form of conservation so perfect that no other large world in the solar system can replicate it. And yet, the story does not end with the surface, because beneath that 4.5 billion-year-old cratered shell, Callisto harbours questions about its own interior that remain genuinely unresolved. The Galileo spacecraft's gravity measurements indicated that Callisto is only partially differentiated, its rock and ice never having fully separated into distinct layers the way Ganymede's did. For a moon this large, that state is difficult to explain. Radioactive heating alone should have provided enough energy to trigger at least partial melting and separation over 4.5 billion years. And the 2025 magnetic induction study, suggesting a subsurface ocean, adds another layer of paradox. How can a world that appears geologically dead on the outside, that apparently never fully differentiated on the inside, still maintain a layer of liquid water somewhere beneath its ancient crust? The answer to that question lies deep within Callisto's interior, in a puzzle that has confounded planetary scientists for decades and that no current mission has yet been able to resolve. What happens when you look below the most ancient surface in the solar system turns out to be even stranger than what sits on top of it. Everything so far lives on the surface. The craters, the multi-ring basins, the sublimation lag, the 4.5 billion year bombardment archive. All of it sits on the outermost shell of Callisto, the part we can photograph, map and analyze from orbit. But planetary science does not stop at the surface. The deeper question, the one that has confounded researchers for more than 2 decades, is what lies beneath that ancient crust. And the answer, or rather the persistent lack of a clean answer, turns Callisto from a merely ancient world into one of the most puzzling objects in the solar system. The tool that opened this mystery is gravity. When a spacecraft flies past a moon, the moon's gravitational field tugs on the spacecraft and alters its trajectory by tiny but measurable amounts. By tracking those trajectory changes with extreme precision, using radio signals bounced between the spacecraft and antennas on Earth, scientists can reconstruct the gravitational field of the moon. The shape of that field reveals how mass is distributed inside the body. A world where heavy material has sunk to the center and light material has risen to the top produces a different gravitational signature than a world where heavy and light materials remain mixed together. The key measurement is called the moment of inertia factor. This is a dimensionless number that describes how concentrated a body's mass is toward its center. A perfectly uniform sphere, with the same density throughout, has a moment of inertia factor of 0.4. A fully differentiated body, where dense rock and metal have separated from lighter ice and settled into a distinct core, has a lower value, typically somewhere between 0.3 and 0.35. Depending on how complete the separation was. The lower the number, the more concentrated the mass is toward the center. The higher the number, the more uniformly distributed the mass remains. NASA's Galileo spacecraft measured Callisto's moment of inertia factor during close flybys in the late 1990s. The result came back as approximately 0.355. That number sits in a peculiar middle ground. It is clearly lower than the 0.4 expected for a completely uniform, undifferentiated body, which means some degree of internal separation has occurred. But it is significantly higher than the values measured for Ganymede, which indicate full differentiation into a metallic core, a rocky mantle, and an ice shell. Callisto's value suggests that rock and ice inside the moon have partially separated but never completed the process. The interior appears to consist of an outer shell of relatively clean ice, perhaps 300 kilometers thick, overlying a deep interior where rock and ice remain incompletely mixed. This partial differentiation is the heart of the puzzle. Callisto and Ganymede are nearly the same size. They have nearly the same bulk density, meaning they contain roughly the same proportions of rock and ice by mass. They formed in the same circumplanetary disk around Jupiter at approximately the same time, from the same reservoir of materials. By every straightforward expectation, they should have followed similar evolutionary paths. If Ganymede differentiated fully, with its rock sinking to form a core and its ice rising to form a mantle, then Callisto should have done the same. The energy sources available to both moons during and after formation, accretional heating from impacts during assembly, radiogenic heating from the decay of radioactive isotopes in their rocky components, and any residual heat from the circumplanetary disk, were broadly similar. There is no obvious reason why one moon should have melted and separated completely, while the other remained only partially sorted. Yet that is exactly what happened. And explaining this divergence, known formally as the Ganymede-Callisto dichotomy, has occupied planetary scientists for decades without producing a consensus answer. The earliest attempts to explain the dichotomy focused on tidal heating. Ganymede participates in the Laplace resonance with Io and Europa, receiving periodic gravitational tugs that flex its interior and generate heat. Callisto orbits outside this resonance and receives no significant tidal energy. If tidal heating provided the additional energy needed to push Ganymede over the threshold into full differentiation while Callisto fell just short, the dichotomy would have a clean explanation. But the timing does not work neatly. The Laplace resonance in its current configuration may not have existed during the earliest epoch of the Jovian system. Some models suggest the resonance assembled gradually as the Moon's orbits evolved over hundreds of millions of years. If the resonance was not in place during the critical early period, when internal temperatures were highest and differentiation was most likely to occur, then tidal heating cannot be the primary explanation for why Ganymede differentiated and Callisto did not. The resonance may have contributed additional heat to Ganymede later in its history, helping to maintain internal activity and drive the grooved terrain formation observed on its surface, but it may not have been the trigger that initiated differentiation in the first place. A second class of explanations focuses on differences in the bombardment each moon experienced during the late heavy bombardment, roughly 700 million years after formation. Research published in Nature Geoscience proposed that the energy delivered by cometary impacts during this epoch could have been sufficient to trigger complete differentiation on Ganymede, but not on Callisto. The key factor is orbital position. Ganymede orbits closer to Jupiter than Callisto does, and Jupiter's gravity accelerates incoming impactors to higher velocities as they fall deeper into the planet's gravitational well. Higher impact velocities mean more energy delivered per collision. According to this model, the cumulative bombardment energy received by Ganymede during the late heavy bombardment exceeded the threshold needed to melt enough of the interior to initiate runaway differentiation, where the sinking of dense rock releases gravitational energy that melts additional ice, creating a self-reinforcing process that drives the separation to completion. Callisto, orbiting farther from Jupiter and receiving less energetic impacts, never crossed that threshold. It absorbed enough energy to partially sort its interior, but not enough to trigger the runaway process. This explanation is elegant, but it depends on assumptions about the intensity and timing of the late heavy bombardment that remain debated. If the bombardment was less intense than the model assumes, or if it was spread over a longer time period allowing heat to dissipate between major impacts, the energy may not have been sufficient to differentiate Ganymede through this mechanism alone. A third and more recent line of investigation approaches the problem from the opposite direction. Instead of asking what extra energy source pushed Ganymede into full differentiation, these models ask what kept Callisto from differentiating, despite receiving what should have been enough radiogenic heat to melt its interior over 4.5 billion years. The radioactive decay of long-lived isotopes like uranium, thorium, and potassium in Callisto's rocky component generates heat continuously. Over billions of years, this heat should accumulate in the interior, eventually raising temperatures high enough to melt ice and allow rock to sink. Models that account for this radiogenic heating often predict that Callisto should have fully differentiated long ago, which directly contradicts the gravity measurements. The solution may involve the efficiency of heat transport. If Callisto's interior convects efficiently, meaning warm material rises and cool material sinks in slow circulation patterns through the ice-rock mixture, heat can be transported from the deep interior to the surface and radiated into space before it accumulates enough to trigger melting. Efficient convection acts as a cooling mechanism that prevents the interior from ever reaching the temperature threshold for differentiation. Whether Callisto's interior actually convects efficiently enough to prevent differentiation depends on the viscosity of the ice-rock mixture, which in turn depends on temperature, composition, grain size, and the proportion of rock to ice at each depth. These parameters are poorly constrained, making it difficult to determine definitively whether convective cooling can explain Callisto's state. A particularly compelling recent development came from research published in 2025, examining how the formation process itself could determine whether a moon differentiates. This work investigated the pebble accretion scenario, where the Galilean moons formed by sweeping up small particles, pebbles, from the circumplanetary disk, rather than by accumulating large building blocks called satellite T-simals. Pebble accretion deposits energy at the surface, where it can radiate away efficiently, rather than burying it deep in the interior the way large impactors do. The study found that if Callisto formed primarily through pebble accretion over a period of roughly 10 million years, its interior could remain cool enough to avoid global melting and differentiation, even while Ganymede, forming slightly earlier or under slightly different conditions in the inner part of the disk, accumulated enough large impactors to trigger melting. This model offers something the earlier explanations lacked: a mechanism that naturally produces different outcomes for two moons of similar size and composition, based solely on the details of their formation process, without requiring special pleading about bombardment timing or tidal heating histories. But the model has been tested only for limited parameter ranges, and it makes predictions about the early circumplanetary disk environment that are difficult to verify with current observations. The honest summary of the Ganymede-Callisto dichotomy as it stands today is that no single explanation has achieved consensus. Multiple plausible mechanisms exist, each supported by modelling work and each facing limitations or uncertainties. Tidal heating differences, bombardment energy differences, formation process differences, and convective cooling efficiency all remain in play. The problem is genuinely unsolved, and it will likely remain so until new data arrives from spacecraft capable of measuring Callisto's interior structure with far greater precision than the Galileo mission achieved. And then there is the ocean. If Callisto's partially differentiated interior were the only puzzle, the Moon would already qualify as one of the most scientifically interesting bodies in the outer solar system. But the magnetic field measurements from Galileo added a second layer of mystery that made the picture far stranger. During several close flybys of Callisto, the Galileo magnetometer detected perturbations in the local magnetic field that were consistent with an induced magnetic signal. Jupiter's powerful and rapidly rotating magnetosphere sweeps past Callisto as the Moon orbits through the planet's magnetic field. If Callisto contains an electrically conducting layer beneath its surface, Jupiter's time-varying magnetic field should induce electric currents in that layer, which in turn would generate a secondary magnetic field detectable by a passing spacecraft. This is the same phenomenon, magnetic induction, that provided the most compelling evidence for Europa's subsurface ocean. At Europa, the induced signal was strong and unambiguous. At Callisto, it was weaker, measured in tens of nanotesla rather than hundreds, and complicated by an unexpected factor. Callisto possesses a surprisingly dense ionosphere, an upper atmospheric layer where molecules have been ionized by solar ultraviolet radiation and by energetic particles from Jupiter's magnetosphere. This ionosphere is electrically conductive, and an electrically conductive ionosphere can also produce an induced magnetic field in response to Jupiter's time-varying magnetosphere, potentially mimicking the signal that a subsurface ocean would generate. For more than 2 decades after the Galileo measurements, scientists debated whether the observed magnetic perturbations required a subsurface ocean or whether the ionosphere alone could account for them. A 2017 study argued that ionospheric induction was responsible for a significant portion of the observed signal, casting doubt on the ocean interpretation. The question remained genuinely open, a frustrating ambiguity that prevented Callisto from joining Europa and Ganymede in the confirmed ocean world category. The 2025 study by Cochrane and colleagues at NASA's Jet Propulsion Laboratory attacked this ambiguity head-on. The team incorporated magnetic data from all available Galileo flybys rather than relying on the subset used in previous analyses. They built detailed computational models of Callisto's ionosphere, accounting for its asymmetry and variability, and used those models to estimate the maximum magnetic signal the ionosphere could plausibly produce. They then constructed over 24,000 forward models of Callisto's interior structure, systematically varying the depth, thickness, and conductivity of a hypothetical ocean layer, while also varying the ionospheric properties. Each model configuration was tested against the observed magnetic data from multiple flybys at different frequencies of Jupiter's driving field. The multi-frequency approach was the key innovation. Jupiter's magnetic field varies at several distinct frequencies, as Callisto orbits through different regions of the magnetosphere. An ionosphere and a subsurface ocean respond differently to these different frequencies because they have different electrical properties and sit at different depths. By jointly analyzing the magnetic response at multiple frequencies, the team could distinguish between the two sources of induction far more effectively than previous single-frequency analyses had managed. Their results were clear. The ionosphere alone cannot explain the observed magnetic signal at all analyzed frequencies simultaneously. Models that include a subsurface salty ocean fit the data significantly better than models without one. The ocean most consistent with the data sits deep beneath the surface, possibly more than 150 kilometers down, with a conductivity consistent with salty liquid water. The finding does not constitute absolute proof. The data still carry uncertainties, and the Galileo magnetometer was not designed for this level of analysis. But the evidence is now substantially stronger than it was before. Callisto very likely harbours a subsurface ocean. This finding creates a paradox that is genuinely difficult to resolve. How can a moon that is only partially differentiated, that shows no surface evidence of geological activity, and that receives no significant tidal heating, maintain a layer of liquid water beneath its ancient crust? On Europa, the subsurface ocean is maintained by tidal heating from the Laplace resonance, which continuously pumps energy into the moon's interior. On Ganymede, the situation is more complex, but a combination of residual heat from differentiation and the insulating properties of thick ice layers may keep water liquid at depth. On Callisto, neither of these mechanisms operates at significant levels. The leading explanation involves antifreeze. If Callisto's internal water contains dissolved salts, ammonia, or other substances that lower the freezing point of the mixture, liquid water can persist at temperatures well below 0 degrees Celsius. Radiogenic heating from the rocky component may generate just enough warmth to keep this antifreeze-laden water from solidifying, especially if the overlying ice shell acts as an insulator, preventing heat from escaping to the surface. The ocean would be cold, salty, deep, and completely sealed from the surface. Not inviting by terrestrial standards, but liquid nonetheless. The implications are significant. If Callisto possesses a subsurface ocean despite lacking tidal heating and full differentiation, it suggests that ocean worlds may be far more common in the outer solar system than previously assumed. Tidal heating has long been considered a prerequisite for maintaining liquid water on icy moons. Callisto's ocean, if confirmed, would demonstrate that radiogenic heating combined with antifreeze chemistry may be sufficient, a finding that would expand the range of bodies potentially harbouring subsurface water to include numerous moons and possibly even large Kuiper belt objects that receive no tidal energy whatsoever. But the ocean also deepens the puzzle of Callisto's interior. If liquid water exists at depth, it means the interior is not uniformly cold and rigid. There must be a thermal gradient sufficient to maintain liquid water somewhere beneath the ice shell. That thermal gradient should also drive some degree of internal convection, which should in turn promote further separation of rock and ice over time. Why then has Callisto not continued differentiating? Why does the gravity field still indicate an incompletely separated interior? One possibility is that the ice-rock mixture in Callisto's deep interior is so viscous due to its composition and the pressure conditions at those depths that convection proceeds extremely slowly, too slowly to have completed differentiation within 4.5 billion years. Another possibility is that differentiation has been proceeding gradually and is further along than the gravity measurements suggest, but that the moment of inertia value is being interpreted through overly simplified interior models that do not capture the true complexity of a partially separated ice rock body with an embedded ocean layer. The uncertainty is genuine, and it is important. Callisto's interior represents an unsolved problem in planetary physics, not because scientists have ignored it, but because the available data cannot yet distinguish between competing models. The Galileo gravity measurements provided only low-order constraints on mass distribution. The magnetic field measurements suggested an ocean, but could not pinpoint its depth with precision. To truly resolve Callisto's internal structure requires multiple close flybys with modern instrumentation, higher resolution gravity measurements, multi-frequency magnetic field coverage, and ideally, radar sounding, capable of directly detecting a liquid water layer beneath the ice. That capability is coming. ESA's JUICE mission, the Jupiter Icy Moons Explorer, launched in April 2023 and is currently en route to Jupiter via a complex series of gravity assists. The spacecraft successfully completed its unprecedented Lunar-Earth double flyby in August 2024 and its Venus flyby in August 2025. It will fly past Earth again in September 2026 and January 2029 before finally arriving at Jupiter in July 2031. Once in the Jovian system, JUICE will perform multiple close flybys of Callisto as part of its tour of Jupiter's large icy moons, using those encounters both for science and to reshape its orbit for eventual insertion into orbit around Ganymede in late 2034. The Callisto flybys will carry instruments far more capable than anything the Galileo spacecraft possessed. The gravity and geophysics package will measure Callisto's gravitational field with sufficient precision to test whether the Moon is truly in hydrostatic equilibrium, a fundamental assumption underlying all current moment of inertia estimates. If Callisto departs from hydrostatic equilibrium, the current interpretations of its internal structure may need significant revision. The magnetometer will characterize the induced magnetic field at multiple frequencies with far better sensitivity and spatial resolution than Galileo achieved, potentially confirming or ruling out the subsurface ocean with much higher confidence. The specifics of what juice will carry to Callisto deserve closer attention because each instrument addresses a different piece of the puzzle, and each is capable of resolving questions that have remained open since the Galileo era. The gravity and geophysics of Jupiter and Galilean moons experiment, known by the acronym 3GM, will use precise radio tracking of the spacecraft during close Callisto flybys to map the Moon's gravitational field at much higher spatial resolution than Galileo achieved. The critical measurement is the degree 2 gravity field, which encodes information about how mass is distributed between the equator and the poles and between the near and far sides of the tidally locked Moon. From this measurement, scientists can calculate the moment of inertia factor with significantly reduced uncertainty. More importantly, they can test whether Callisto is actually in hydrostatic equilibrium, the assumption that the Moon's shape has fully relaxed to match its rotation and tidal state. Every existing estimate of Callisto's internal structure assumes hydrostatic equilibrium because the Galileo data were not precise enough to test this assumption directly. If Callisto departs from equilibrium, meaning its shape retains a memory of some past state rather than reflecting current conditions, then the moment of inertia value derived from gravity data would need to be reinterpreted, potentially changing our understanding of how differentiated the interior actually is. The JUICE magnetometer, designated JMAG, will characterize Callisto's induced magnetic field with sensitivity and spatial coverage far exceeding the Galileo magnetometer. JMAG is designed to separate the various contributions to the magnetic environment around Callisto, including Jupiter's background field, the induced field from any subsurface conducting layer, the contributions from the ionosphere, and perturbations from the surrounding plasma environment. By measuring the magnetic field at multiple points along each flyby trajectory and across multiple flybys, occurring at different phases of Callisto's orbit through Jupiter's magnetosphere, JMAG will sample the induced response at multiple driving frequencies. This multi-frequency capability, the same approach that made the 2025 Cochrane study so powerful, will be applied with hardware specifically designed for the task rather than repurposed from 3-decade-old Galileo data. If a subsurface ocean exists, JMAG should be able to constrain its depth, thickness, and conductivity with far greater precision than any previous analysis. The Radar for Icy Moons Exploration Instrument, designated RIME, may provide the most dramatic result of all. RIME is an ice-penetrating radar sounder operating at a center frequency of 9 MHz, designed to probe the subsurface structure of the icy Galilean moons to depths of approximately 9 kilometers with a vertical resolution of roughly 30 meters in ice. While the primary targets for deep subsurface sounding are Europa and Ganymede, where the ice-ocean interfaces may lie within the instrument's penetration range, RIME observations at Callisto will reveal the structure of the upper ice shell in unprecedented detail. If the ice shell contains internal layering, buried craters, compositional boundaries, or structural transitions between different ice phases, RIME will detect them. In the most optimistic scenario, if Callisto's ice shell is thinner than current estimates suggest, or contains high porosity zones that allow radar penetration to greater depths, RIME might detect reflections from the ice-ocean interface itself, providing the first direct measurement of where liquid water begins beneath an ancient icy surface. Even if RIME cannot reach the ocean directly, its measurements of the upper ice shell will provide ground truth for the thermal models and structural models that currently rely entirely on theoretical calculations and indirect constraints. Knowing the actual structure of the upper few kilometers of Callisto's crust, rather than inferring it from crater morphology and surface spectroscopy, would represent a transformative advance in understanding this moon. The radar sounder may be capable of detecting the ice-ocean interface directly, providing the first unambiguous measurement of ice shell thickness on any of the Galilean moons. JUICE will also study Callisto's surface composition, topography, and thin atmosphere with modern instruments, filling in details that the Voyager and Galileo missions could only sketch. The combined dataset from these flybys will transform our understanding of Callisto from a world known in broad outlines to one characterized in genuine detail. For the first time, scientists will have the tools to determine whether Callisto's partially differentiated state is real or an artifact of insufficient data, whether the subsurface ocean exists and how deep it lies, and whether the ancient surface hides surprises visible only at resolutions the older missions could not achieve. But JUICE will arrive at Jupiter more than 5 years from now. The Callisto flybys will occur over a period spanning several years after arrival. The results will take additional time to analyze and publish. The answers to questions that have lingered since the Galileo mission in the 1990s will not arrive until the mid-2030s at the earliest. Callisto's mysteries are not going to be resolved quickly, which is fitting for a moon that has been waiting 4.5 billion years for someone to pay serious attention. In the meantime, Callisto continues to orbit Jupiter in its slow, solitary path, circling the giant planet once every 16.7 Earth days at a distance of nearly 1.9 million kilometers. It is too far from Jupiter to participate in the tidal resonance that powers its siblings, too geologically quiet to generate headlines, too ambiguous in its interior to have been definitively classified as an ocean world before 2025, and too enormous, too ancient, and too scientifically rich to deserve the obscurity that has settled over it like the dark sublimation lag that blankets its cratered surface. The question that remains, the one that touches not just on Callisto but on how we allocate attention across an entire solar system full of worlds, is why this particular moon ended up forgotten. Not merely overlooked during a busy news cycle, but systematically deprioritized across decades of planetary exploration. The answer involves more than just Callisto's geological quietness. It involves the way spectacular moons actively steal attention from preserved ones, the way mission planning responds to public excitement rather than archival value, and the uncomfortable realization that one of Jupiter's 4 original moons, one of the very first objects ever observed orbiting another planet, became the sibling that nobody in the family talks about. Understanding how that happened reveals something important not just about Callisto, but about the biases built into how humans decide which worlds deserve our curiosity. There is a pattern in how humans allocate attention across the solar system, and once you see it, you cannot unsee it. We are drawn to worlds that do things, worlds that erupt, worlds that crack, worlds that hide oceans and hint at life. We build missions to those worlds, we name documentaries after them, we fund telescope time to study them, we put their images on magazine covers and in classroom posters and in the opening sequences of science videos. The worlds that do things become famous. The worlds that preserved things become footnotes. This is not a failure of science. Scientists understand perfectly well that Callisto matters. The peer-reviewed literature on Callisto spans decades and includes work by some of the most respected researchers in planetary science. Papers on its cratering record, its internal structure, its surface composition, and its potential subsurface ocean appear regularly in major journals. The Galileo mission devoted multiple flybys to it. JUICE will study it with modern instruments. No credible planetary scientist would claim that Callisto lacks scientific importance. The knowledge exists. The appreciation exists within the specialist community. But scientific importance and public visibility are two very different currencies, and they do not trade at equal rates. The way we communicate planetary science to the broader world is shaped by narrative instincts that strongly favor action over stillness, mystery over certainty, and danger over preservation. A volcano erupting on Io produces images that require no explanation. The visual is the story. Lava, fire, destruction, a world tearing itself apart in real time. A fractured ice shell on Europa invites the most emotionally compelling question in all of science. Is there life out there? A magnetic field on Ganymede earns the automatic interest that comes with uniqueness. the only moon in the solar system with that particular distinction. Each of these features translates effortlessly into a headline, a documentary pitch, a social media post, a reason to care. Callisto's value does not translate that way. Try summarizing it in a single sentence for someone who is not a planetary scientist. The most heavily cratered surface in the solar system. That sounds like damage, not discovery. A 4.5 billion-year-old bombardment record preserved by geological inactivity. That sounds like nothing happened. A partially differentiated interior that challenges models of moon formation. That sounds like a technical problem, not a revelation. Each of these statements is true and each is scientifically profound, but none of them fires the same neural circuits that a volcanic eruption or a hidden ocean fires. Callisto's importance lives in what it kept, not in what it does. And preservation is an inherently quiet virtue in a culture that rewards noise. This bias is not unique to planetary science. It operates everywhere humans make decisions about what deserves attention. In ecology, we pour conservation resources into charismatic megafauna, while less photogenic species that play equally critical roles receive a fraction of the funding. In journalism, stories of action and crisis lead the news, while stories about stability and preservation rarely make the front page, even when they represent phenomena of equal significance. Callisto is the planetary equivalent of a building that survived every earthquake, every war, every urban renewal project for 4.5 billion years, and was then described as boring because it never burned down. The absence of fire is precisely what made it irreplaceable. But we do not have good instincts for recognizing value in absence. We notice what is present, what is active, what demands a response. We overlook what is still, what is intact, what simply endured. The mission history of the outer solar system reflects this bias with uncomfortable clarity. Consider how exploration resources have been distributed among Jupiter's moons. The Galileo mission studied all 4 Galilean satellites, but its most celebrated results came from Io and Europa. The volcanic monitoring of Io produced some of the most visually spectacular data in the history of planetary exploration. The detection of Europa's induced magnetic field, suggesting a subsurface ocean, reshaped the priorities of an entire scientific discipline. Ganymede's intrinsic magnetic field and complex surface geology generated significant scientific interest. Callisto's flybys produced valuable gravity and magnetic data, but the results were ambiguous enough to prevent definitive conclusions about its interior, and the surface images, though scientifically rich, showed more of what the Voyager missions had already revealed: craters upon craters upon craters. After Galileo, the divergence accelerated. NASA's next major mission to the Jovian system, the Europa Clipper, is dedicated entirely to a single moon. Europa earned its own $5 billion spacecraft because the possibility of a habitable ocean beneath its ice generates the kind of scientific and public excitement that justifies that level of investment. The Europa Clipper will perform dozens of close flybys of Europa, mapping its ice shell, sampling its tenuous atmosphere, and searching for evidence of geological activity that might indicate communication between the ocean and the surface. It is one of the most ambitious planetary science missions ever undertaken, and it exists because Europa possesses a quality that Callisto lacks: the ability to make people dream about finding life somewhere other than Earth. ESA's JUICE mission will study Callisto, but Callisto is not the primary target. JUICE will perform multiple Callisto flybys, and those flybys will produce transformative science. But the mission's ultimate destination is Ganymede, where it will enter orbit in late 2034 and spend the final phase of its operational life studying the largest moon in the solar system in unprecedented detail. Callisto serves as a scientific waypoint and a gravitational stepping stone on the path to Ganymede. It will receive far more attention from JUICE than it has received from any mission since Galileo, and that attention is overdue. But the mission architecture itself reflects the priority hierarchy. Ganymede gets an orbiter, Europa gets a dedicated mission, Callisto gets flybys. This is not a criticism of how missions are planned. Mission selection involves extraordinarily difficult trade-offs among scientific objectives, engineering constraints, cost limitations, and political realities. Every mission that flies represents years of effort by thousands of people and billions of dollars of investment. The decisions are made carefully, and the scientific returns from Europa Clipper and JUICE will be immense regardless of how many flybys each moon receives. The point is not that Callisto deserved a dedicated mission and was unfairly denied one. The point is that the pattern of exploration reveals the same bias that operates in public attention more broadly. Worlds that promise action, life, uniqueness and spectacle attract resources more easily than worlds that promise preservation, archives, and deep historical records. Callisto's scientific case is compelling within the research community, but it does not generate the visceral excitement that drives mission selection in a world where funding depends on public and political support. The Saturn system offers a parallel that sharpens the contrast. When the Cassini spacecraft discovered active geysers erupting from the south polar region of Enceladus, a tiny moon barely 500 kilometers across, the scientific community pivoted. Enceladus became one of the highest priority targets in the solar system almost overnight. Plumes of water ice and organic molecules spraying into space from fractures in the ice shell provided direct evidence of a subsurface ocean and raised the possibility of hydrothermal activity on the seafloor. A moon that almost no one outside of planetary science had heard of before Cassini became one of the most talked about worlds in the solar system, because it was doing something. It was active. It was spraying material into space. It was offering a potential window into a habitable environment that a spacecraft could sample without even landing. Contrast that with Callisto, which is nearly 10 times the diameter of Enceladus and has been known since 1610. Callisto does not spray material into space. It does not crack its surface with tectonic forces. It does not produce any observable evidence of internal activity. Its potential ocean, if it exists, lies buried beneath more than 130 kilometers of solid ice, completely sealed from the surface, inaccessible to any plume sampling mission. Callisto offers no shortcut. Studying its ocean, confirming its existence, understanding its chemistry, all of this requires orbital measurements, sophisticated data analysis, and patience measured in decades. There is no erupting geyser to fly through, no fracture to peer into, no dramatic visual to broadcast. The science is there, but it hides beneath stillness, and stillness does not compete well in the attention economy of planetary exploration. Titan, Saturn's largest moon, provides yet another comparison. Before the Cassini mission and the Huygens probe that landed on its surface in 2005, Titan was largely mysterious, shrouded in a thick orange haze of nitrogen and methane that prevented any clear view of the surface. The mystery itself generated enormous interest. What was hiding beneath that atmosphere? The Huygens landing revealed a surface shaped by rivers and lakes of liquid methane, dunes of organic particles, and a landscape unlike anything else in the solar system. Titan earned its fame through revelation, the dramatic unveiling of a hidden world. NASA's Dragonfly mission, a rotorcraft lander scheduled to arrive at Titan in the 2030s, will extend that exploration. Callisto has no veil to lift. Its surface has been visible to every telescope and spacecraft that pointed in its direction since Galileo Galilei first spotted it 4 centuries ago. The craters are right there, in plain view, covering every square kilometer of terrain. There is no dramatic unveiling possible. The surface is exactly what it appears to be: ancient, battered, uniform, and quiet. The drama, if you can call it that, lies in understanding what that quietness means, in recognizing that the absence of change is itself the phenomenon worth studying. But narrative drama requires tension, surprise, and reversal. Callisto's story is one of continuity, endurance, and refusal to change. It is a story that resists the narrative structures we instinctively impose on the worlds we explore. This brings us to the deeper question, the one that Callisto's situation forces us to confront. What do we actually value in planetary exploration? If the answer is spectacle, then Callisto will always rank below Io. If the answer is the search for life, then Callisto will always rank below Europa. If the answer is record-breaking uniqueness, then Callisto will always rank below Ganymede. But if the answer includes preservation, if we value the ability to read the deep history of the solar system in surfaces that were never overwritten, then Callisto rises to a position that none of its siblings can match. No other large body in the solar system offers what Callisto offers. Its cratered surface is the most complete record of early outer solar system bombardment that exists anywhere. Its partially differentiated interior preserves information about the formation conditions of the Galilean moons that Ganymede's full differentiation destroyed. Its potential subsurface ocean, if confirmed, would demonstrate that liquid water can persist in the outer solar system without tidal heating, expanding the range of worlds that might harbour hidden water far beyond the currently recognised ocean moons. Consider what this would mean in practice. The current census of confirmed or strongly suspected ocean worlds in the solar system is short. Europa leads the list, with magnetic induction evidence so strong that a dedicated NASA mission was built around investigating its ocean. Ganymede appears to harbour a deep ocean sandwiched between layers of high-pressure ice based on Hubble Space Telescope observations of its Aurora and Galileo magnetic data. Enceladus has a confirmed global ocean beneath its ice shell, demonstrated by the Cassini spacecraft's detection of tidal libration and the direct sampling of ocean-derived material in its erupting plumes. Titan possesses a subsurface water ocean inferred from Cassini gravity and rotation measurements, though Titan is better known for its surface lakes and seas of liquid methane. Each of these confirmed or strongly suspected ocean worlds shares a common feature. They all receive significant tidal heating from gravitational interactions with their parent planets or neighbouring moons, and that tidal energy is considered a critical factor in maintaining liquid water against the deep cold of the outer solar system. If Callisto's ocean is confirmed, the logic changes. Callisto receives negligible tidal heating. Its ocean, if it exists, is maintained primarily by radiogenic heat from long-lived radioactive isotopes in its rocky interior, supplemented by the freezing point depression caused by dissolved salts or ammonia in the water. These two factors, radioactive decay and antifreeze chemistry, are not unique to Callisto, they are universal. Every icy body in the solar system that contains a rocky component possesses radioactive isotopes that generate heat. Every icy body that incorporated salts or ammonia during its formation contains potential antifreeze compounds. If these two factors together are sufficient to maintain liquid water on a body as geologically inactive as Callisto, then the threshold for ocean formation in the outer solar system drops dramatically. Neptune's moon Triton, captured from the Kuiper belt and now orbiting in the outer solar system, far from any tidal resonance capable of generating significant heating, becomes a stronger ocean candidate. Triton already shows signs of geological activity, including cryovolcanic features observed by Voyager 2 during its 1989 flyby, but the question of whether it possesses a current subsurface ocean remains open. If radiogenic heating plus antifreeze chemistry is sufficient, Triton's rocky interior may generate enough heat to maintain a liquid layer. Pluto, visited by the New Horizons spacecraft in 2015, showed geological features on its surface that some researchers have interpreted as evidence for a past or present subsurface ocean, including the nitrogen ice-filled Sputnik Basin and extensional tectonic features on the surface that could result from the gradual freezing of a subsurface liquid layer. If the Callisto model applies, Pluto's modest radiogenic heat budget, combined with ammonia or other antifreeze compounds in its interior ice, could sustain liquid water even at the extreme cold of the Kuiper belt, 40 times farther from the Sun than Earth. The implications extend further still. The Kuiper belt contains numerous large icy bodies, Eris, Haumea, Marke, Sedna, and potentially many more awaiting discovery, each with rocky components generating radiogenic heat and compositions, likely incorporating freezing point depressing volatiles. If the tidal heating requirement is removed, every one of these distant worlds becomes a potential ocean world. The solar system might contain not 4 or 5 ocean moons, but dozens or even hundreds of bodies harbouring subsurface liquid water, most of them in the cold outer reaches where sunlight is feeble and tidal forces are negligible. The census of potentially habitable environments would expand from a handful of well-studied moons around Jupiter and Saturn to a population spanning the entire outer solar system, fundamentally changing the statistical landscape for astrobiology. All of this hinges on whether Callisto's ocean is real. The 2025 Cochrane study provides the strongest evidence to date, But the question will not be definitively settled until JUICE or a future mission measures Callisto's interior with sufficient precision to confirm or rule out a liquid water layer directly. That confirmation, if it comes, would do more than add one more name to the list of ocean worlds. It would change the rules governing how that list is constructed, and Callisto, the quiet moon that everyone forgot, would be the reason. Each of these contributions is unique to Callisto. None of them can be obtained from any other body. And each of them exists precisely because Callisto did nothing. Because it never erupted. Because it never resurfaced. Because it never participated in the orbital resonance that gave its siblings their dramatic qualities. Because it sat quietly in the outermost Galilean orbit for 4.5 billion years, absorbing impacts, preserving its original interior structure, and maintaining whatever thin layer of liquid water its radiogenic heat and dissolved salts could sustain, while the rest of the Jovian system put on a show. The irony is perfect, and it is irreducible. Callisto's silence is simultaneously the reason it was forgotten and the reason it matters. The same geological inactivity that prevented it from generating headlines preserved the scientific archive that makes it irreplaceable. The same orbital isolation that excluded it from the tidal resonance powering its siblings protected it from the internal heating that would have erased its ancient surface. The same lack of surface renewal that made it visually monotonous created the most information-dense cratered terrain in the solar system. Every quality that pushed Callisto to the bottom of the public attention hierarchy is a quality that elevated it to the top of the preservation hierarchy. The two rankings are mirror images of each other, and recognizing that inversion is the key to understanding why this particular moon deserves a fundamentally different kind of attention than the one we have been giving it. There is something uncomfortable in this recognition. It suggests that our instincts about which worlds matter are systematically biased in ways that can cause us to miss genuinely important objects. If Callisto, one of the 4 original Galilean moons, nearly the size of a planet, the most heavily cratered body in the solar system, a possible ocean world, can be quietly forgotten for decades simply because it lacked visible activity, then what other worlds have we overlooked for similar reasons? How many objects in the solar system carry scientific value that we have failed to recognize because that value is encoded in stillness rather than spectacle? The question extends beyond planetary science. It touches on how we assign importance to anything. We live in a culture that equates value with activity, significance with visibility, importance with noise. The things that demand attention receive it. The things that sit quietly, preserving their contents, enduring without complaint, maintaining their integrity across vast stretches of time, these things tend to be overlooked until someone finally pauses long enough to examine what they contain. Libraries do not compete well against theatres. Archives do not trend on social media. The loudest painting in the gallery draws the crowd, but it is not necessarily the one that preserves the most history. Callisto is an archive. It has been an archive since the solar system was young, collecting impact records on its surface while every other large world around it was busy erasing its own past. 4.5 billion years of bombardment history, written in craters ranging from sub-kilometre bowls to 3,000-kilometre ring systems, preserved in a surface that never experienced a single volcanic eruption, a single tectonic event, a single episode of large-scale resurfacing. That record is still there, still readable, still encoding information about the size, velocity, and frequency of objects that struck the Jovian moons during the most violent chapter of solar system history. No other large body kept this information intact. Every other comparable world chose, through the blind physics of its internal heat and orbital dynamics, to overwrite its archive and start fresh. Callisto did not choose preservation any more than Io chose volcanism. These are consequences of physics, not decisions. But the language of choice is useful here because it highlights what was gained and what was lost. Ganymede gained tectonic complexity, full differentiation, and an intrinsic magnetic field, but lost most of its ancient bombardment record. Europa gained a subsurface ocean and a compelling case for habitability, but lost its entire cratering record to continuous resurfacing. Io gained the most volcanically active surface in the solar system, but lost every trace of its impact history. Each moon traded its past for its present. Callisto made the opposite trade, not by choice, but by circumstance. It sacrificed activity for its archive. It gave up geological drama and received in return the most complete deep-time record available on any large world. Whether that trade was worth it depends entirely on what you value, and for planetary science, the answer should be clear. Archives of the early solar system are irreplaceable. Geological activity, however spectacular, is ongoing and can be studied wherever it occurs. But the first billion years of bombardment history, recorded in the surfaces of worlds that formed alongside the planets themselves, that record exists in exactly one place at this scale and level of completeness: Callisto. The JUICE mission will begin to unlock this archive with modern tools in the 2030s. Its Callisto flybys will provide higher resolution imagery of the cratered surface, better gravity measurements of the interior mass distribution, more precise magnetic field characterization of the potential subsurface ocean, and compositional mapping of the surface materials that the Voyager and Galileo missions could only partially survey. Each dataset will refine our understanding of what Callisto preserved and why. Each measurement will add detail to the picture of a world that kept its secrets not through complexity, but through simplicity, not through activity, but through endurance. But even before JUICE arrives, Callisto deserves a different kind of recognition than it has historically received. Not the breathless excitement reserved for worlds that might harbour life. Not the superlative-driven attention given to worlds that break records. Something quieter and more durable. Recognition that a world can be scientifically extraordinary, not because of what it does, but because of what it refused to destroy. Recognition that preservation, across timescales so vast they make human civilization look like a momentary flicker, constitutes its own form of significance. Recognition that one of the largest moons in the solar system became easy to forget, not because it lacked value, but because its value is the kind that requires patience, attention, and a willingness to look past spectacle towards substance. Callisto orbits Jupiter today exactly as it has for 4.5 billion years. Slowly, quietly, far from the tidal resonance that drives its siblings, far from the radiation belts that pound Europa's surface, far from the volcanic fury that continuously resurfaces Io, it completes one orbit every 16.7 Earth days, turning the same face toward Jupiter in a tidally locked rotation that has persisted since the moon was young. Its surface receives a thin rain of micrometeorites and the occasional larger impact that adds one more crater to a terrain already saturated with them. Its dark lag of sublimation residue thickens imperceptibly, century by century, as ice sublimates from the surface and leaves behind a growing veneer of rocky dust. Deep beneath the ancient crust, radiogenic heat from decaying isotopes may still maintain a thin layer of salty liquid water, sealed away from the vacuum above by more than 100 kilometers of solid ice. Nothing about this scene is dramatic. Nothing about it would make a compelling movie poster, or a viral social media post, or a breathless news headline. It is simply a giant moon, almost the size of a planet, carrying the oldest intact surface in the solar system on its back like a weight it never asked for and never tried to set down. The real shock is not that Callisto is large. Several moons are large. The real shock is not that Callisto is old. Everybody in the solar system is old. The real shock is that one of Jupiter's 4 great moons, one of the original worlds that proved planets could have satellites, one of the objects that helped overthrow the geocentric model of the universe, became the one that everyone quietly stopped talking about. And the reason they stopped talking about it is the same reason it became one of the most scientifically valuable surfaces we can still study. It preserved its age instead of erasing it. It kept its history instead of making new history. It endured instead of performing. In a solar system full of worlds competing for attention through eruptions, oceans, atmospheres, and magnetic fields, Callisto competed through silence. And silence, it turns out, is the one quality that no other giant moon was willing to offer. Every scar on that battered surface is a sentence in a story that began when the solar system was still forming, a story that every other large world edited, revised, or deleted entirely. Callisto kept the original draft. It is still there, 4.5 billion years later, waiting for someone to read it carefully enough to understand what it says. That draft is the most complete record of deep planetary history preserved on any large world we have ever found, and it belongs to the giant moon that everyone quietly forgot.